All right, here we go. The day is a fun lesson. Okay, so we're going to continue our exploration of areas of two-dimensional shapes. Remember, next chapter will be 3 dimensions. Let's see, we've done triangles, we've done quadrilaterals, all of them. Well, what's left are all the other shapes, and so it makes this big jump between doing a 3-sided polygon to a 4-sided polygon to doing all polygons, and you'll understand why after the lesson. Just one theorem. This one is it is the easiest looking formula ever, and in the most complicated one at the same time. All right, so just one thing today. It's a simple formula. It's usually challenging to use it though. So think about this. Polygons. Remember, polygons are closed plane figures constructed at segments joined at their endpoints. Triangle being the first one, quadrilateral being the second one, pentagon, hexagon, so forth and so on. So here we have a triangle, right? 3 sides on a flat surface, segments that have been joined at their endpoints. And we have a formula for area of that one, 1/2 base times height. If we think about regular polygons, we've had this definition before. Let's see, a regular polygon, well, it's got to be a polygon, so it meets that, but a definition of a polygon. But it also means that all the sides have the same measurement. So if one side is 5, all the sides are 5. And then it also has a second statement. It says that all the angles have the same measurement. Now, a lot of people, when they read this definition, think that the sides have to have the same measurement as the angles. That's not what it's saying. It's simply saying, I'll use a triangle, for example, that if it's a regular polygon, all the angles are the same measurement and all the sides are the same measurement. And that's what makes it regular. And today, we'll be doing areas of regular polygons. So how much purple is right there? So it turns out, interesting feature of regular polygons, that regular polygons can all be inscribed inside of a circle. So there's your triangle, there's your square, there's your pentagon. Now these are all regular polygons right here. So the last one there doesn't fit perfect, but it's just my mistake on PowerPoint. That's not a mistake of a regular polygon there. So all regular polygons can be inscribed inside of circles, or a circle can circumscribe any regular polygon. And you had that, that was one of the constructions that you did on the test. And many other shapes can also be inscribed inside. But for irregular polygons, here's an irregular pentagon right here. And notice that this particular irregular pentagon cannot be inscribed inside of a circle. And now, I just so we're clear, I'm not saying that you can't inscribe a non-regular shape inside of a circle. So, for instance, if I extended that side to right here, and then another side from there to there, and then connected from that to that. So I'm ignoring, let's see, I'm ignoring this part right here. Notice I still have 1, 2, 3, 4, 5 sides. So there's an irregular pentagon inside of the circle. But what I'm saying is that not all irregular pentagons or polygons in general can be inscribed. And most irregular polygons cannot be inscribed. Now, two quick exceptions. The 2 exceptions are rectangles can always be inscribed, and triangles can always be inscribed. And so I remember that was the one construction you had on the last test. But for most other irregular polygons, they cannot be inscribed inside of a circle. So key takeaway number 1 is that if you're regular, you can draw a circle around it, touch all the vertices. Let's add a few vocabulary words to our understanding here. So the first one I'm going to say is that if you take the center of a regular polygon, it is also the center of the circle that circumscribes that regular polygon. So we call that center of the circle. We also call it the center of the regular polygon. So that's our first definition. And as always, pause the video. I'm moving on. Okay, second definition, if I extend a radius from that center dot right there, remember that's the center of a circle. So if I extend a segment to the side of the circle, I've made a radius. Well, notice that that would also intersect a vertice of the regular polygon. So since we called that the radius of the circle, we will also call that the radius of the regular polygon. So it's the distance from the center to its vertex, and it's also the radius of that circumscribed circle. Okay, couple more. Okay, same idea. This is going to look exactly the same, but notice there will be a slight difference. Regular polygon, circumscribed center. And this time I'm not going to go to a vertice. I'm not going to make a radius. I'm going to drop a perpendicular. There's the radius. But what I'm going to do is I'm going to drop two of those, and I'm going to talk about the angle in between right there, that angle right there. So if you think about the circle, that would be a central angle of the circle. So we'll also call it the central angle of the regular polygon. So that's the angle formed by two radii drawn. It's got to be two consecutive vertices, but it's two things. It's the central angle of the circle, the circumscribed, and then it's also the central angle of the regular polygon itself as well. All right, last one. This one's new. All right. Same idea. I'm just going to drop a that black dotted line right there. That black dotted line drops straight down. Notice it's not a radius. I didn't extend it past the polygon. And it is perpendicular, and we are going to give it a fancy name, and its fancy name is the apothem. So the apothem of a regular polygon. So we just call it an apothem. This is that perpendicular distance from the center to any side of the regular polygon. And those are our definitions for today. Now we're going to work on our formula. Quick note, the two most screwed up or messed up concepts by students is the difference between the radius and the apothem. So don't confuse your apothem, that's the red portion, with your radius. So apothem is the perpendicular distance from the center to a side, and a radius is a distance from the center to a vertice of the regular polygon. All right, second note, if we pick any starting point and don't construct just a tiny central angle, go all the way around to where we started. So let's say that's our starting point, and we go all the way around, it makes a circle. Therefore, we've gone 360 degrees. Keep that in mind. We're going to use it here in a few minutes. All right, third and final note. Okay, we need abbreviations for these three words: radius, apothem, and side length. Well, we're going to use the obvious ones. Side length is going to be an S. Apothem is going to be a little a. Remember, capital A means area, and radius, obviously, we'll get an R. So RAS for those three words. Okay, cool. So I'm not going to do a formal two-column proof right here. We call this a proof plan. So if you were asked to do a proof, and before you're on a test and it's an important test and you got to write a proof, just like if you were asked to write a couple paragraphs or maybe a couple pages on a specific topic, you would do an outline first. So this is kind of like an outline of a proof. We're going to put our major ideas down here. We're going to follow a logical sequence. We're just not going to put it in a nice formal way. So this is called a proof plan. Is this how you can do a proof? Oh, certainly. If you were ever to turn this in for a test or a proof plan, it's easy to convert these into a paragraph proof. Just talk through what you just state for everyone, or turn into a two-column proof as well too. So this is called a proof plan. All right, think about this. So take any regular polygon. Yes, triangles are the easiest one to work with. I'm gonna pick any regular polygon, and I chose an octagon. But I'm not saying that this proof only works for octagons, because I'm not making any claims other than it's a regular polygon. Remember the definition of regular polygon: the sides are the same distance and the angles are all the same distance. So I'm going to consider just one triangle of all the triangles that I could make from the center to a vertice. So I'm going to make a central angle. See what I did right there? So that's one of, let's see, if it's an octagon, there's 8 of those, right? If I could go all the way around, I'm just going to consider one of those. I'm going to label one of the sides, and it's apothem. So S for side, remember, an apothem is that perpendicular distance between the center to any of the sides of the regular polygon. So there's my apothem. Okay, now what? Well, let's consider the area of that one triangle right there that I just drew. In order to consider the area of that one triangle, we got to use the area formula, 1/2 base times height. Well, the base there is clearly S, and the height is A, so my formula would be 1/2 S times A. So that would be the area of that one black triangle right there of the octagon itself. Now, if I consider the entire polygon now, well, since all of those black triangles would be exact, it's regular, right? So all the radii would be equal, all the sides would be equal, all the apothems would be equal. So I can prove that any of those triangles, if I drew some more, let's say I drew that one, I could prove that that triangle and that triangle are congruent easily by SSS. Remember, I'm going from the center to a vertice, so all the radii would be equal, and since it's a regular polygon, all the sides of the polygon will be equal. So by it's another, and I'm not talking about that S right there that's on the screen, but you know the 5 bullets there, SSS, all the triangles would be congruent. So that means that every one of these black triangles right here have the same measurement in terms of area as well. So therefore, I just need to take my formula, area of z equals 1/2 SA, and multiply it by how many triangles I have. Well, how many triangles I have is how many sides I have as well, too. So if I let n represent the number of sides, I simply need to take the area formula and multiply it by the number of sides, because that's how many triangles there are. There's 8 of those black triangles. So therefore, since I let n represent the number of sides, my formula would be area is equal to n times the area of one of those triangles. Now, I'll do a little algebra trick here. I'm just going to move that n next to the letter A. I'm sorry, next to the letter S. There we go. So it says 1/2 NSA. And now what I'm going to ask you to do is consider the following. If we think about the perimeter of any polygon, and especially if it's a regular polygon, then that would be, well, let's see, it would be the length of one of the sides times how many sides there are. And I just let n represent how many sides there were. So the perimeter of any polygon would be take all those s's and add them up. Well, there's 8 of them. In other words, there's n of them, because remember, n is how many sides, or triangles in this case. So that would be P for perimeter is equal to N times S. And well, look at the formula we just wrote before that and why I moved the N next to the S. Now I have N and S, and I can do a quick substitution, and I can write 1/2 PA, and that's our formula. And that was a proof, just a talking proof. All right, so that's what theorem 11.6 says. It says that if you had, and this only applies to regular polygons, if it's an irregular polygons, unfortunately, you're going to have to break that up into recognizable shapes that you have formulas for, and then go from there. Typically, you break it up into triangles. However, if it's a regular, and this goes for anything from a triangle all the way up to, an infinitely sided figure, right? 1/2 PA. So P for perimeter, A for apothem, well, I guess you're doing a calculator, PA divided by 2. Either one of those forms. The PA divided by 2 is not in the book, but most people that type these values into a calculator would do that form right there on the right. Okay. Quick caution, it's really easy to mistake the apothem with the radius. You're like, well, how could I mistake that? Because the formula doesn't use the radius. True, but as you see in my examples, we're going to have to use the radius in order to find the apothem, typically. And so therefore, it's really easy to screw those two things up. A is, remember, the perpendicular distance between the center and the side, and R is the distance between the center and a vertex. All right, so don't mistake your A and your R. All right, that's your apothem. What is the radius good for? Well, it's going to help us figure out what the apothem is when they don't tell us what the apothem is. I think I've got 2 examples here that show that. All right, so hold that thought. Before geometry, areas of triangles, we did areas of quadrilaterals, right? Remember, this is from, let's say, 9th grade on, before that. So from K through 9, you probably did area first sometime around the 4th grade. You've never calculated area for anything larger than a quadrilateral. And now we have formulas for everything as long as it's a regular polygon. All right, that's our form, 1/2 PA. So this is for those of you that are Lord of the Rings fan. All right, so these are 2 examples. These are definitely going to be challenging problems, so get ready. Here we go. All right, so it says calculate the area of this regular hexagon, and notice the only thing listed there is the apothem. Well, that's great. I need to know the apothem, but I also need to know the perimeter, and the perimeter isn't listed, P for perimeter. So I can throw that 9 in for A, but I need to find the perimeter, and how in the world am I going to find the perimeter if all I have listed is one value right there, 9? These are typically how these problems work. They're either going to give you the radius or the apothem or a side length, or maybe they give you the perimeter itself. So as always, high school geometry, when in doubt, make some triangles. So we're going to make a triangle right there. It's a regular hexagon. That means all the angles are the same, and all the side lengths are the same. And since I need to find the perimeter, well, the perimeter would be 6 times one of the side lengths, right? So if the apothem was 9, I'm going to focus on one of those triangles. So the left triangle, right? I can do the right triangle, be fine. So I'm going to focus on that one left triangle right there. I'm pointing to it. And if I could calculate the side of that, if I doubled that side, right, then I would have the entire one of the sides of the hexagon. I know the apothem. I don't know the radius, right? But in order to do this, well, let's see, what options do I have? It is a triangle, and I'm trying to find side lengths. So I'm trying to think, well, trig would probably be an option. Trig and Pythagorean theorem would be the 2 options. So sometimes Pythagorean theorem is the easiest way to go. If you got 2 side lengths, always use Pythagorean theorem, as long as it's a right triangle, and it will be for these. But you could also use normal trig as well, too. Just make sure your calculator is set for degrees. All right. Remember that second note that I said that if you have any starting point, if you go around, you go in 360 degrees. I'm about to use that idea. All right, so here we go. So since I either want to use trig or Pythagorean theorem, in order to use Pythagorean theorem, I would need 2 sides. I only have one side, so I'm kind of forced to use trig right here, or special right triangles, one of the 2. Remember, special right triangles is still trig. All right, let's see. Let's find that one angle right there. Why that angle and why not the other angle? You can find any of the other angles. You're going to see that this one's a little bit easier to do. All right, so that angle, we know that if we go in a full circle, we've gone 360 degrees. Now, be careful what I'm talking about right here. I'm talking about, we'll start off with this angle that goes from here to here, all the way across. We know since it's a isosceles triangle. How do I know it's isosceles? Because the red lines there, those are both radii, and remember the radii are all equal. So it is a isosceles triangle, and we know if we drop a perpendicular from the vertex of a isosceles triangle, that this angle right here will be cut in half. Okay. So let's find that angle. So 360, there are 6 of those triangles, right? We're not talking about the small one, we're talking about the big red one right there. So there's 6 of those triangles. So let's see, that would be 6 goes into 30, that would be 60 degrees. And that would be the entire green thing would be 60 degrees, right? So we want half of that. So let's see, half of 60 degrees would be 30 degrees. Oh, it's a special right triangle, right? Why half of 60? Because remember, that would go all the way across, and where the yellowest point is just one of those angles, so it's 30 degrees. So it is a special right triangle. Could we use trig, sine, cosine, tangent? Absolutely. Lots of kids like to use that instead of special right triangles. But as soon as I see a 30, I'm thinking special right triangles. So it's a 30, 60, 90. So there's my generic 30, 60, 90. I got the value 9 right there. And let's see, I need to find the bottom. I need to find, I'll draw it for you right here. Remember, I'm trying to find the perimeter because I already have the 9 for the apothem. What I need is the perimeter. The perimeter would be this side plus this side, so forth and so on. That side right there would be, let's see, this piece of the triangle. So if the entire thing was S, then this side would be half of S. And the other side would be also half of S. So if I could just find out what what this side is right here, double it, then I would have the whole thing multiplied by 6 because there's 6 sides and that would be done. So that's my goal here. So looking at my special right triangle, well, I know that that bottom there is A. In other words, this is A. Well, this would be A. It looks like a 9, but it's supposed to be an A. That's A. So if I doubled A, I would have the entire side, and then I can multiply by 6. If I said that too fast, back it up and make sure you understood what I meant there. If not, let's go. All right, so what is A? Well, I don't know, but I do know that the apothem is 9. And let's see, on my special right triangle, the apothem is this value right here. So I'm going to take that value right there, A root 3, right? Because remember, I'm trying to find the perimeter. So I'm trying to find that part and double it, and I get the whole thing. So I basically should have clicked the button rather than talk through this. I have it all here. Okay, so back to this. So I know that 9 is equal to A root 3. And now I'm going to solve for A. So I don't square both sides because then I would get A squared. I'm going to divide both sides by root 3. So if I divide both sides by root 3, the root 3 on the left would cancel. We don't like having roots in the denominator, so remember that trick. We multiply both in the top and the bottom by root 3. On the bottom, you'd get root 9, which is 3. So we get 9 root 3 over 3, reduce. 9 divided by 3 is 3, so we get 3 root 3. That's what A is. So A is 3 root 3. So let's see, that would be this piece right here. And the other side would also be 3 root 3. So 3 root 3 plus 3 root 3 is 6 root 3. And so there's my S value for side, but I need the perimeter. So let's see, how many of those sides do we have? We have 6 of them. So 6 times 6 is 36. So the perimeter is because perimeter would be the number of sides times the S length, and the S length is 6 root 3. So 6 times that would be 36 root 3. So I can throw in for the value P way over there on the right here. So this value right here is this value, right? Well, 36 root 3, right? I probably have that written right. Oh, I did. There we go. Now just do a little bit of math here. Let's see, half of 36 is 18, and 18 times 9 is a big number. And remember, we're doing area, it's in square units. All right, so that was a lot of work. I just want to point out, remember, we had 3 options to do this. Let's see, we had, well, technically we only had 2 options. But when you do these problems, you're going to have 3 options after the initial startup. You're either going to use Pythagorean theorem, or you're going to use special right triangles, or you're going to use trig. A lot of kids are like, hey, I'm just going to use trig every single time. But remember, in order to use trig, then you need to have at least one angle, right? And so that process of this right here of taking 360 dividing by the number of sides and then taking half of it to find that value right here. I'm getting a lot of green here. To find half of it, remember that's where a 30 came from right there. So that never changes. So Pythagorean theorem, special right triangles, or trig, sine, cosine, tangent. Okay. I think we need to do another one. All right. So that is a lot of work. Here's another one. So the previous one, let's see, we started off with the apothem. This time we're going to start off with a radius right here. Same basic process. You're going to make a triangle. You're going to figure out some angles, and you're either going to pick special right triangles, Pythagorean theorem, or trig. Let's go to town here. All right. So let's see. Got a radius is 10. See, the process was I need the perimeter and I need the apothem. I have none of that. I have neither the perimeter nor do I have the apothem. So I need to figure out either. It doesn't matter the order that you do this. I usually go for the apothem first if I don't have it, but you could do the perimeter first if you wanted to. So we set up one triangle, drop a perpendicular, and that red perpendicular is going to be the apothem. So that's going to be your A value. It's not labeled right here. We take the 360 divided by how many sides? There were 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's see, 360 divided by 9 would be 40, but I'd have to take half of that to see where the arrow's pointing right there. So that's 20. So now, no, that's not a special right triangle. So now I have to go with trig. So sine, cosine, tangent. So remember, sine, cosine, tangent, SOHCAHTOA. Let me write this out. I just showed you the answer. Let's see. So apparently I like green today. TOA. Sine, cosine, tangent. Remember the small letters are going to be the sides of the triangle. So if we know, I need a new color. Getting tired of green. So if I know 20, then this side right here would be the opposite. And the 10 would be the hypotenuse, H. I'm not going to write HYP. And luckily for us, adjacent and apothem use the same letter. Just be ready, right, for that. Okay. So, and I have to find both the opposite and I need to find the apothem as well too. So I need to find both of those. It doesn't matter which one you find first. All right. So if I want to find the apothem first, and I'll circle this in, I'm running out of colors here. If I'm trying to find the apothem, then that's the adjacent, and the number I have is the hypotenuse. So A and H, A and H. A and H would be cosine. If I want to find this is going to turn into a color nightmare here. If I want to find the side length right here, that would be the opposite, and that would also be the, since 10 is the only value I'm given, the opposite and the hypotenuse, and that would be your sine. So I think I do this the side first. I thought I did the apothem first. So let's see. Sine of 20 would be the opposite over the hypotenuse. I chose the value x to represent opposite. You can choose whatever. You can use an s if you like. I probably wouldn't choose s because that would be, and really you're doing half of s right there. And then this is just a calculator drill. Multiply both sides by 10. Grab your calculator. Make sure it's in degrees. 10 sine 20. You're going to have to round. And I'm getting about 3.4. Make sure you do that and verify that so you're getting what I'm getting. All right, so what did I just calculate? I calculated in green here. I just calculated this portion right here. So I'm going to erase it, all of my horrible handwriting right here. So I have some room here. Okay, so I just calculated this, and remember, this is approximately 3.4. So double that, all right? The other side's 3.4. We get 6.8 for the side, and that's approximate value. More decimals actually are better, but I think tonight for homework says rounding yours decimal or 10th. Let's see, how many sides do we have? I think it was 9 of them, right? Count 1, 2, 3, 4, 5, 6, 7, 8, 9. So I need to do 9 times 6.8, and that is 61.2. Notice I changed the equal to approximate. Now I just need to find the apothem. You got two options now. I've got a side of 3.4. I got a side of 10. I could use Pythagorean theorem. So it would be what? 10 squared minus 3.4 squared, and take that answer and take the square roots. Or I could use trig again. I'll show you trig since we're already set up for trig. So let's see, in relationship to the 20 degrees right here. Oops. I just showed you the answer again. In relationship to the 20 degrees right here, if I'm finding the apothem is the adjacent, and the radius is the hypotenuse. So I got an A and an H. A and an H is cosine. So same idea. Cosine of 20 is equal to A over 10. Multiply both sides by 10. Grab your calculator and away you go. You type that into your calculator, you get about 9.4. Once again, verified to make sure you're getting what I'm getting. All right, do we have everything? Because that's the apothem. I sure do. So A is now 9.4, and now it's just one big calculator problem. If I were doing this by hand, I would do 61.2 times 9.4 divided by 2. You want to do 0.5 times 61.2 times 9.5. That would work. 9.4. That would work as well. So that's what I got for my answer. Hopefully you got the same thing. So those were two the process is the same each time. They're either going to give you the radius, or they're going to give you the apothem, or they potentially could give you the side length. If they gave you the side length, for instance, on this one, if they gave you the fact that the side was 6.8 right from the very start, you could take half of that and find that this was 3.4, and then you could find the apothem from there. Okay. Same process though with the angle measurements though. 360 divided by how many sides, and then take half with the angle. So it's either going to turn into trig, special right triangles, Pythagorean theorem. All right. Wow. Oh, and now I have a nice little slide that says exactly what I just said. So tonight for homework, it's either going to be special right triangles or Pythagorean theorem or the trig functions that are listed right there. Okay. 1 through 12 for homework tonight is your standard. Our book loves its tables. So little r means radius, little a means apothegm, little p means perimeter, and capital A means area. And as always, it follows the same pattern when they give you exactly what you need. So what do you need for this formula? You need the apothegm and you need the perimeter. So the first couple, they give you both of those, and then they erase one of the a or the little p, and then they give you some of the other ones, and it just turns into a little bit of an algebra / trig problem from there. So if you run into any problems, once again, don't hesitate, ask me the questions. But if not, that'll do it for today. I will catch you next class.